Hi, kids. So, how was your calculating? I know mine was pretty great too. All right, so I used unified atomic mass units. If you did this, that's fine. If you did this and you want to get my number, okay, all you have to do is take your mass and multiply by that number right there, or you can do it in just leave it in kilograms, and that's okay too. It's okay. But I got this unit here. Okay. So when I add this plus this plus this, I got this, and so if I add all of the protons and neutrons and electrons up individually, this is the mass that I get. But if you look on this page in your notebook, you will see, if you look up carbon 12, carbon 12 has its atomic mass is exactly 12.0000 unified atomic mass units, okay? Which means there is a mass defect of just this number here. So my mass defect is this 0.0989376. So then it's like, well, what the heck happened? Well, because I add all these up and I'm off by this much mass. Well, guess what happened? That mass got turned into energy that's holding my nucleus together. Okay, and that's where all that energy went. All that energy went into, all that mass went into that energy. And if you want to figure out exactly how much energy that is, okay, well, if I take this number right here and I multiply by, so like, hey, this 0.0989376, if I plug that in for here and I multiply by c squared, I would get my energy. But you know what? Rather than doing it that way, I know that the one atomic mass unit is 931 mega electron volts. So if I multiply this divided by c squared, if I multiply this by 931, I'm going to get the number of mega electron volts that I'm going to get. So let's do that. I'm going to take that number, I'm going to subtract 12. So I got my 0.09 blah, 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 and then times 931, so that it would be 92.11 mega electron volts. And this is what's called the binding energy. So that when I fuse, hence why it's called fusion, when I fuse 6 protons, 6 neutrons together, okay, this amount of energy is the amount of energy that's holding it together. So if I want to break a carbon nucleus apart, I need at least that much energy there. Now, on the AP test, you got to be careful. Sometimes they'll ask you for binding energy. That's your answer. Sometimes they'll say binding energy per nucleon. Well, then how many nucleons do I have? I have 12. So if you were to take this number divided by 12, that would be the binding energy per nucleon. So just answer the question that's asked. But there you go. And this idea of E equals mc squared is really, like with Oppenheimer and the movie and the bomb and stuff like that. That's really where, hey, look, a little bit of mass, you can get a ton of energy out, and that's where you got the ton of energy out. Okay. One last thing, just so you guys got it. The force that's actually holding those nucleons together, okay, is called the strong nuclear force, because, physicists were not very creative people. So it's like, hey, this force is really strong. So it's going to be the strong nuclear force. Because remember, okay, that my red were my protons. Well, these protons don't want to hang out next to each other. They want to repel. So, if what happens is so that my nucleus can be stable, well, then I need to add a bunch of neutrons there so that I add more. If you look, hey, look, right there, I'm adding more strong nuclear force, which in this model is represented by hot glue. And you have a stable nucleus as long as the strong nuclear force holding everything together is stronger than the electrostatic force trying to push it apart. Well, eventually, if your nucleus gets too big, because strong nuclear force only happens when nucleons are touching, well, where electrostatic force happens anytime you have same charge, charges around each other. And eventually, if your nucleus gets too big, the strong nuclear force can't hold it together, and your nucleus is unstable, and you get nuclear decay, and there you go. So I hope that makes sense. There you go. Bye, kids. Oh no.